So in the last video, we discussed the idea of the accept-reject algorithm and particularly established the validity of the algorithm itself and further also discussed a few insights on why the algorithm is the way it is. Just to go back to what the actual algorithm for the accept-reject methodology is we're in the premise where we have a target distribution F with that has a density small f, and we want to obtain samples from this distribution. The algorithm is such that it generates one draw from this distribution, and calling this algorithm multiple times can give us multiple draws. The way we actually call this methodology or this algorithm is that we choose a proposal distribution G. Now, how this choice is informed, we'll discuss a little bit in the next video. But we choose a proposal distribution G, which will be a valid proposal if two things hold. The first is that the support of the proposal needs to be larger than the support of my target distribution. So the set of values for which the proposal distribution is positive, the proposal density is positive, needs to be larger than the set of values for which the target density is positive. And then second, we need the proposal density such that the supremum of the ratio f by g measured over the support of f needs to be finite. Okay, and that a bound in the supremum needs to be available to us. So a C is the bound that needs to be available to us, and it needs to be finite. So the key goal really is to find such a C such that this ratio is bounded for all over the support of the target. And once we do that, then we draw uniform random variables. Then we draw a proposal draw from G. So G is my proposal distribution, and I obtain Y as my proposed value. If this value is good, I want to accept this value. And if this value is not so good, I don't want to accept this. And so I want to repeat the process until I get an acceptance. And good values meaning that the random draw, a uniform draw, should be less than equal to f of y by cg of y. And then we accept, otherwise we reject that value and then restart the loop. And the number of times this algorithm is expected to run before it returns a value, we also discussed is C. The upper bound C that we use in the ratio is the mean number of loops to get an acceptance. Okay, so this is what we discussed up until the previous video. And in this video, we're going to go look at a few different examples of the accept-reject method. So the first example is that of a beta distribution, so a beta target distribution. So for a beta target distribution, let's say I'm considering beta 4, 3. So the two parameters of the beta distribution here are 4 and 3, where we'll recall that the density of a beta distribution is basically the gamma function of the sum of these two parameters, so that's 7, divided by the product of the individual gamma functions of those parameter values, times x to the power 4 minus 1 and 1 minus x to the power 3 minus 12, where these 4 and these 3's are coming from these parameters. It's always going to be critical in the accept-reject algorithm that we look at the support of our distribution. And the support of our distribution in this case is 0, 1, x in between 0, 1. So that means if I want to choose a proposal distribution for this beta situation, then I need to choose a proposal distribution that has support exactly 0, 1 or larger than 0, 1. Okay. Now, the larger the support I choose, the more wasteful it is, because any value proposed outside of my support of the target distribution will immediately not be accepted. All right. So I need to choose as small a support of the proposal as possible. And in this case, that becomes 0, 1. And a default reasonable proposal on 0, 1 is the uniform distribution on 0, 1. Right? So the uniform density function is basically g of x equals 1 for all x in 0, 1. Right? So that's a very simple density function. And in this case, script x is equal to script y because my supports are the same. Okay. Now for this choice of g, what I then need to do, so at this point, I I have a potential proposal, right? But for it to be a valid proposal, I need to actually check whether sup f by g over 0, 1, if that's positive or not, right? So that's my next task. So let's take a look at sup f by g. Now, g of x is nothing but 1 in this case, and so this just becomes sup of f from with x being in 0, 1. And in this case, f of x, my target density is this exactly here. Now, the following is a trick we'll be using very, very often in this course, is if we want to find a supremum or a maximum, then we can, instead of finding the maximum of this function, we can take log of the function for which we want to find the maximum, and then find the value of x that maximizes the log. Right? And the reason is that because f is log is a increasing in monotone function, the value of x that maximizes f of x is the same value of x that maximizes log of f of x. So maximizing log f of x is the same thing as getting the maximizer of my f of x. So we take log and then we'll take a derivative set to 0 to find a critical point. Right? So we take log. Log of these numbers is just a constant, so I don't want to really write that down. So I can just write constant plus 3 log x plus 2 log 1 minus x. Right? That's what happens when we take log here. And then I take a derivative with respect to x. When I take a derivative, this becomes 3 by x, and then I get 2 by 1 minus x with a negative sign because of the minus when I take the derivative here. And I set that to 0. And from here, I can very quickly see that this implies that a critical point is x equals 3 by 5. Now, at this point, we only have the critical point. So to confirm that the critical point is a maximum, we should take a second derivative and verify that it is positive. Now, I will sometimes skip this in the notes, particularly when taking a second derivative is straightforward and it's not, it would not be a good use of our time in these videos, but you should always verify. Okay, so we would expect you to verify for any given problem that if I want to maximize something, the second derivative is indeed negative. And in this case, when I take a second derivative, well, this becomes minus 3 by x squared, and this becomes still is minus 2 by 1 minus x squared, and both of these terms, when x is between 0 and 1, are negative, and so this is overall a negative value. Okay. Thus, the maximum of f of x occurs at x equals 3 by 5. Right? So that means that that's where the maximum occurs. So I can take this x equals 3 by 5, this is the critical value, and I plug it back in the sup of f of x, because that's really exactly where the supremum occurs. Right? So this means that the sup of f by g, which is equal to the sup of f of x, is exactly equal to, I plug in x equals 3 by 5 to see what I get, and that's 60, 3 by 5 cubed, 2 by 5 squared, and that I'm going to call C, right? Okay, so now the main thing I've actually understood is that C is finite, so accept reject is possible. Right? That's the main thing that we have actually learned. And now the value of C is going to inform us about how efficient the algorithm will be. Right? How many times would I need to propose from this in the algorithm to get one single acceptance on average? Right? That's what C informs us. Okay. So in this case, if I were to implement the algorithm, I draw Y from uniform 0, 1. This is the uniform check. and then I draw the proposal value y from uniform 0, 1. So the first one, sorry, is a u, second one is a y, and these two should be independent of each other. Which means I can't use the same uniform draw in this step and this step. These have to be two separate and independent uniform draws. They shouldn't have anything to do with each other because we actually use the independence in our proof of accept reject as well. Now, again, if u is less than equal to this ratio, then x is equal to y, else go to step 1. Okay? So let's actually see what this turns out to look like in implementation. So now we're going to look at some R code where I'm going to write, I set a seed. Again, the set a seed is the pseudo random number generation seed setting that we do. And now what we're going to do is we're going to make a function. So here, beta AR is a function that will return one draw from beta 4, 3. This is the idea. Okay. So now C is equal to the constant that I have just determined. So I set C in the beginning. I have an indicator accept, which tells me if it's 0 that I have so far I have not accepted, and when it will turn to 1, it will mean that I have accepted it. Then I have a counter, which currently is 0, which is going to calculate the number of loops it took to actually get an acceptance. Now, while I have not accepted, my loop is, or from here to here, is going to keep on running, right? So while I have not accepted, first increase my counter, which is going to count the number of loops. Then draw my uniform draw, which is the uniform check. So this is U. Then draw my proposal. This is my Y from G step. Okay. Now, once that's done, now I have to do my check. This is my So this is my ratio of f of y by c g of y. So notice in this case, g is just 1. So there is the denominator is simple. And then f of y is nothing but d beta evaluated at trop, where the first parameter is 4 and the second parameter is 3. And now if u is less than equal to ratio, then I accept. And actually, in this case, I just return inside the function, and I return C, prop, and counter, which means together combine prop, the proposed value, which is my Y, because that's the value I want to return, and counter. Okay. So then when I call this function, it's going to give me both the proposed values and the number of loops that the algorithm takes. Right. Now, I'm going to now call this function multiple times. So my goal is to get, in this line over here, we'll basically indicate that my plan is to get x1, x2, x 10,000 IID from beta 4, 3. Right? This is what I'm aiming to do. And all of those values are going to be saved in SAMP. So SAMP is a vector where all of these values are going to be saved in SAMP. Right. Okay. And then my counts, or the number of loops, each of the calls to draw the random variable is going to be saved in counts. And now for I going from 1 to n, I'm going to basically repeatedly draw a value from beta AR, and I'm going to save it in foo. Remember, foo is what I use as a dummy name when I'm the actual object I'm not interested in, and I can rewrite every single time. So I'm using something temporarily, then I call it foo. Then foo's first location, first object, which is my prop value or my y value, will be saved in SAMP I, and the second one is saved in counts. Okay. Now, once this finishes, then I have at this point, gotten x1, x2 up until xn IID from my desired distribution, and I have gotten a sequence of numbers that tells me how many loops the algorithm took to understand how efficient it is. Now what I'm going to do to verify that I've actually done things correctly and things are happening well, I'm going to plot this line, plots the estimated density function from the samples. So if I give it samples, it's going to basically draw the estimated density functions from the samples. So the actual density functions of the samples is a beta 4,3, and this is going to estimate it from the samples itself. But on top of it, what I'm going to do is I'm going to draw the actual density function that's done by d beta. And I'm going to draw the actual function on a grid of values between 0 and 1. All right. And I add a legend as well to understand which is the true one and which is the false one. And what I see is that the true one is the one in red over here. Okay. And then the black one underlying here is the actual estimates from is the estimated density from the accept reject algorithm. And we see that the true one and the estimated one are very close to each other. They're a little bit different. They're a little different, but they're a little different only because the black curve is estimated. When I say it's estimated, that naturally means that it comes with variability, right? Because it's being estimated, it comes with natural variability. So this curve will change from seed to seed and from implementation to implementation, the black curve. The truth curve, the red curve will remain the same, but the black curve will change from implementation to implementation. So some natural variability is always going to be expected, right? So this is an idea that this is a demonstration that our algorithm, our function does indeed work because our estimated density from the samples is very similar to the true density. But further, what I can also do is also compare the counts or the number of loops the algorithm took. Now see that we calculated this number, 60 times 3 by 5, blah, 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 is 2.0736. So that means this is the expected number of loops the algorithm is supposed to take, right? To give us one acceptance. Now, in the count vector, this is a vector where in every part in the counts vector, in every sort of slot of the vector, this has the number of loops it took. Number of loops the algorithm took to get an acceptance for the first time that the function was called, and then for the second time that the function was called, and then for the third time that the function was called, right? Every single time that the function was called. So if I just take an average of these counts, that should try to approximate C, and that's exactly what happens. When I take an average of counts, this is 2.0776, which is very close to the actual value of C. Again, if you do this another time, then what you'll see is that counts and the mean of the counts will be slightly different because this is also random because these are geometrically distributed. All right. So that's one example of the accept reject algorithm. Let's look at another example. This one is our favorite normal distribution. Okay. And what our goal now is to actually, first we'll try and sample from the normal 0-1 distribution. Now, what would be a good proposal for the normal 0-1 distribution? So first I want to implement accept reject, and I'd like a good proposal distribution. Now, when I'm thinking of proposal distributions, particularly when the support is not bounded, when the support is all over R or goes to infinity or minus infinity in any one direction, then it is really good to think of proposals that have fatter tails than our target distribution, or recall in the last video, we discussed that if I have a distribution like this, then I would like a proposal distribution that actually has, fatter tails, so that in the tails it's higher than the underlying distribution of interest to us. And so that is so that f by g can remain bounded. So keeping that in mind, we want to choose a proposal distribution. Now recall the target density is the standard Gaussian density, which is f of x equals 1 by square root 2 pi e to the power minus x squared by 2. Now, this is the Gaussian distribution. And we know, hopefully we recall, that the student's t distribution has the right support. Now, what I mean by the right support is that the support is r, right? And has fatter tails. Now, fatter tails meaning that in fact they don't go down, they don't drop down to zero. The density function does not drop down to zero very quickly as you go farther and farther away from zero. Okay, and the fattest t distribution, the fattest in the tails t distribution is the Cauchy distribution. Okay, which corresponds to this corresponds to degrees of freedom equal to 1. Okay, so that means a reasonable proposal distribution for us to consider is the Cauchy distribution, for which the density is 1 by pi 1 by 1 plus x squared. Okay, and we want to find the supremum of the ratios of the densities. Okay, that's what we want to find. The C. So that means I want to actually find the sup of f by g over my whole space of x and r. But before I find sup, I want to actually look at what f by g looks like. And f by g looks like pi by square root 2 pi 1 plus x squared e to the power minus x squared by 2. Okay. Now, intuitively, what I see is that the exponential function decreases down to 0 very fast compared to any polynomial function. Okay. So the exponential e to the power minus something positive reduces to 0 very quickly compared to any polynomial function. And so this is really why this quantity remains bounded and does not convert or does not diverge to infinity. But let's see if we can find a supremum. So first I take the derivative, and in the same way as the beta example, I'm going to take the derivative of the log of the distribution. Oh, sorry, not the distribution, log of the ratio. So I define L of x to be the log of f by g. Now this is just some constant, and that's log of this constant, plus log of 1 plus x squared minus x squared by 2. And now I take a derivative, and this implies that the derivative of this term is 2x by 1 plus x squared. The derivative of this term gives us minus x. I set it to 0. Okay. Now, if I solve the above, right, and now it's straightforward for you to see that if I solve the above, then the supremum is going to occur at both x equals minus 1 and x equals 1. And because both f and g are symmetric about 0, f1 by g1 is equal to f of minus 1 by g of minus 1, right? Because they're both symmetric about 0, so f1 is equal to f of minus 1 and g1 is equal to g of minus 1. Which means now that I know that supremum of x and r of f by g is equal to, I can choose either minus 1 or plus 1. I choose plus 1. Is f by g1, which is square root 2 pi e to the power minus x squared, and that is approximately 1.746. Okay, and as I've discussed, all I need is an upper bound. So just for some numerical stability in implementation, I can set c to be 1.80. Okay. And similarly, as we did for the beta example, you can go back to the beta example code and change the f and g's to appropriately to actually implement this with c equals 1.80. And this also tells us, this value c also tells us that we expect 1.80 loops for one acceptance. All right, we'll move on to a two-dimensional example. Okay, but that I guess we can do in the following video, because we really want to take special care into the two-dimensional example.